Our third curricular outcome is comparing the source direction and strength of vector fields as determined by a test object. So if you were to have, say, a proton and an electron, we can figure out what force we have in between them using Coulomb's law, which we will go through in much more detail in Physics 30. But both the electric force and the gravitational force have the same sort of pattern. So they both have a constant out front, and that just represents sort of the strength of the force in the context of our unit systems. Because these aren't going to be equal units, kilograms are the base unit for mass and coulombs are the base unit for charge, they are not directly comparable. If you dig deeply enough into particle physics, you will get the dimensionless coefficients that represent the field sources. And we will find that the electric field is far, far more powerful than the gravitational field. Then we have the appropriate charges for that field, electric charges for the electric force, and masses for the gravitational force. And that term in our denominator, the distance squared, is identical. So generally speaking, we do have the difference in forces, and the electric field is much stronger and much easier to manipulate. Sure, we could throw a ball in the air, but our arm is not going to be powerful enough to keep that ball from dropping back on the surface. We can't keep it in the air indefinitely with the strength of our arm. Whereas you could take a balloon and rub it on your head for a few seconds and stick it to a wall and it'll stay because of the induced charge. So the electric and magnetic forces are comparable in strength, although if you just have a single charge for electrons, you get a force that's completely divergent, whereas with magnets you always have to have both poles, so it completely curls around back in on itself. With the gravitational force, it is exclusively attractive to the best of our knowledge.